Last problem, number 6. So it's eigenvalues, eigenvectors, and diagonalization, all that fun stuff. So given the following matrices, notice you're given all of the eigenvalues, you're given all of the eigenvectors, so it really just depends on, or you're given most of them, so it really just depends on what you're trying to get. But we essentially understand that AX equals lambda X. Okay, that is the core of these eigenvalue problems. So find the values Q, R, and S such that x1, x2, x3 are eigenvalue vectors of matrix A. Okay, so there's unknowns in here that we need to solve for. So what we do is we take A, multiply them by each x. Q11, so that should be equal to 0 times this vector. So I don't really need to multiply, that looks like a 9. I don't really need to multiply all of these. I just need to do my first row and first column. So negative 4q minus 7 plus 3, that should equal to 0 times q11. So essentially, 0 equals negative 4q minus 4, so therefore q equals negative 1. Do that for the rest of them. Negative 4, negative 5, negative 5, negative 7, 0, negative 7, 3, negative 5, 2. For my next one, it's going to be 4, 5, and R. Same idea. I don't need to technically do it for all of them. I can only do it for the last one. So negative 20 minus 35 plus 2R. And that's the same as negative 9 times this vector. So negative 20 minus 35, so negative 55 plus 2R equals negative 9R. Or negative 55 equals negative 11R, so R equals 5. And then my last one is 4s and 3. So if I do the middle one, it's going to be negative 20 plus 0 minus 15, and that's equal to my third eigenvalue, which is 7 times 4s3. So therefore, negative 35 equals 7s, and s equals negative 5. And there we go. I've solved for all of them. You could go through and you can do all your multiplication, but notice it doesn't matter what this one is or this one. It doesn't matter what that value is, these ones or these ones, because those have no impact on whether or not my unknown is. They're just going to tell me that the answer here is going to be 0, 0. This one here is going to be this one would be negative 36, and this one would be negative 45. This one would be 7 times 4 is 28, and this one would be 21. And it just would tell me that it's 7 times whatever the number is, or your eigenvalue whatever times whatever that number is. For B, is the matrix diagonalizable? Yes, because lambda 1 is not equal to lambda 2 is not equal to lambda 3. Because 0 is not equal to negative 9 is not equal to 7. You have 3 distinct eigenvalues. C, use the determinant, state whether the matrix of eigenvectors is singular or invertible. Your eigenvector matrix is going to be these vectors. So it would be negative 1, 1, 1 in your first column, 4, 5, 5 in your second column, and then 4, negative 5, and 3 in your third column. It says use the determinant, so you can go ahead and use the determinant, calculate it however you want. For this one, I'll use the modified fish method. So it's going to be negative 1, 5, 3, so negative 15, plus 4, 5, 1, or 4, 5, negative 1, so negative 20. Plus 4, 1, 5, positive 20, minus Negative 1, negative 5, and 5, so 25, plus 4, 1, 3, 12, plus 4, 5, 1, 20. So negative 15 minus, this would be 2, 3, 4, 5, 57. So the determinant here is going to be equal to negative 72. It's not equal to 0, therefore it's invertible. Which means it's non-singular, which means your matrices, your vectors are linearly independent, which is something we already knew because otherwise it wouldn't be diagonalizable, and our eigenvalues are all different. For D, it looks complicated, but it's not. Without calculations, write down the product of x inverse A, x. Okay, x inverse times A times x is just your diagonal matrix with your eigenvectors, or your eigenvalues plugged in. So if this here is x, the eigenvalue for this one was equal to 0. The eigenvalue for this one was equal to negative 9. The eigenvalue for this one was equal to 7. Okay, if you plugged in your x vectors differently in a different order, your lambda here should reflect that. Okay? And there we go. That is our last problem.